So we begin Unit 3 in Math 151 with Section 7.1, which deals with radicals and fractional exponents. Alright, so first we just have a few definitions here. The first being a number b is a square root of a, alright, and then there's the notation for it, b equals the square root of a, if b squared equals a. So there's a couple of things to note here, because there's a difference between if I just ask you a question like, what are the square roots of 16, right? So if the question is, what are the square roots of 16, you would tell me, all right, well, 4 is a square root of 16 because 4 squared equals 16, but also negative 4 is a square root of 16, right? And again, why do these work? Because 4 squared gives you 16, right? But also negative 4 squared gives you 16. So there are actually 2 square roots of 16. However, if I give you this and I say, all right, evaluate this, the square root of 16, what is it? It's actually equal to 4, right? So when you see that that radical sign there, the square root symbol, the radical sign, you assume that you're taking what's called the principal or positive square root, right? Now, if you want to do this, right, negative square root of 16, then that's going to be negative 4, okay? And that, of course, would be called, not surprisingly, the negative square root, okay? So what's important to note here are just all the different perfect squares, right? The numbers whose square roots are natural numbers, right? So which numbers are actually perfect squares? One would be a perfect square, 4 would be a perfect square, 9 would be a perfect square, 16, which we just did, would be a perfect square, then 25 would be a perfect square, 36 would be a perfect square, 49 is a perfect square, 64, and then 81, and then 100, and then 121, and then 144, and those are the first 12 perfect squares, right? So 1 is a perfect square, again, because 1 squared is 1. So the square root of 1 is going to be 1, right? 4 is a perfect square because 2 squared is 4. So the square root of 4 is going to be 2, right? And this pattern is going to keep following all the way through here. Like 49 would be the square root of 49 equals 7, right? And then 144 would be the square root of 144 equals 12, so on and so forth. So those are the first 12 perfect squares, right? So that should not be really anything new to you. Now, one thing to note here is that I gave you the principal square root, right, the negative square root. What if I gave you something like, oops, this, the square root of negative 16, right? Now, what you'd be looking for here is a number that when you multiply it by itself, right, that when you square it, it gives you negative 16. The problem with that is, of course, if you square a positive number, you get a positive. If you square a negative number, you get a positive. So there's no number that you can actually square that's going to give you a negative value. Therefore, this square root of negative 16 is actually it's not a real number, right? And then at the end of this chapter, in section 7.6, we'll actually learn that this thing, the square root of negative 16, is actually an imaginary number. Right? So there's a couple different things you can say about this at this point. The square root of 16, we can say it's not real, we can say it's imaginary, or we could even say, I guess, that it does not exist. Right? But we don't call it undefined. Right? Undefined is different. Undefined really means like it has no mathematical meaning. But actually the square root of negative 16 does have a mathematical meaning, which we will get into in section 7.6, like I say. All right? So that's your basic idea of square roots. And then, of course, cube roots is very similar. The difference being that with a cube root, you have to find the number that when you cube it, you get the value. Okay? So, like, if I took the cube root of negative 27, does that exist, actually? Right? Because the square root of negative 27 would not be a real number. But the cube root of negative 27 actually is a real number, and it actually happens to be negative 3. And that's because if you do negative 3 cubed, you actually get a negative 27. Right? So the cube root of negative 27 is actually negative 3, and then the cube root of positive 27 is actually positive 3. And again, the reason being is that 3 cubed equals 27. Right? So you can actually take the cube root of a negative number. Right? The cube root of a negative number is actually a real number. Right? The square root of a negative number is not real, but the cube root of a negative number is real. And this little 3 here, that's what's known as the index. It tells you which root you're taking, right? So if there's no value there, you assume it's a 2, right, which would be a square root. If there's a 3 there, you assume it's a cube root. Right? I mean, there's no assumption. It's clear, right? There's a 3 there, so it means it's the cube root. Okay? And similarly with, as with perfect squares, we have perfect cubes, right? So 1 would be a perfect cube, but actually in this case, it's actually positive or negative 1. They're both perfect cubes, because 1 cubed is 1, negative 1 cubed is negative 1, right? And then the same thing holds with 2. 2 cubed would be 8. Negative 2 cubed would be negative 8. So positive negative 1, positive negative 8, positive negative 27, positive or negative 64, and then positive or negative 125. Right? Those are the first 5 perfect cubes. Right? And it's interesting to note that 64 is actually both a perfect cube and a perfect square. Right? So, like with 1, the cube root of negative 1 is negative 1. Right? The cube root of negative 1 is negative 1. With 8, the cube root of 8 would be 2. Right? I mean, here, the cube root of negative 64 is negative 4. Right? And so on and so forth. Okay? So there's your cube roots. So we looked at square roots and cube roots. So now here we actually have a third definition, which is a more general definition of what's known as an nth root. Right? So b is an nth root of a, and there's again the notation of it, b equals the nth root of a. So what would that be? That would of course be, continuing the same pattern that we had above, right? It was a square root if b squared equals a. It was a cube root if b cubed equals a. So it's going to be an nth root if b to the n power equals a. Right? So square root and cube root are just more specific examples of nth roots. Right? It could be a fourth root, it could be a fifth root, it could be a sixth root, so on and so forth. So the fifth root of 32, right? The fourth root of 81 what would the fifth root of 32 be? Well, you're looking for a number that when you raise it to the fifth power, so the number times itself 5 times will give you 32. So that's actually going to be 2, because 2 to the fifth equals 32, right? And the fourth root of 81, here you're looking for a number that when you raise it to the fourth power, multiply it by itself 4 times, you get 81. So this is actually going to be 3. And again, it's because 3 to the fourth equals 81. And as with square roots, what's going to happen is any even root, so like say the sixth root of -1, this is again not real, because again the idea would be, can you multiply anything by itself 6 times and get a negative number? No. So what ends up happening is any even root of a negative number is non-real, imaginary, right? And the key there, of course, is even, right? You can take the odd root of a negative, like for example, the fifth root of -32, that does exist, right? It's actually -2. And again, that's because -2 to the fifth will give you -32, right? But any even root of a negative number is non-real, right? So that's just the general definition of an nth root, okay? And then we have the definition of the absolute value. Now, when you actually learn absolute value initially, you probably say the absolute value is really like a distance, right? You'll say it's the distance of a number from 0. So like, what's the absolute value of -5? It's 5, because -5 on a number line is 5 spaces away from 0, right? But the actual definition of the absolute value is this. The absolute value of a number x is actually equal to the square root of the number squared, right? So think about why this is true, because let's say you have the square root of, I don't know, 4 squared, right? The square root of 4 squared is going to be equal to the square root of 16, which is really just 4, right? So in this case, when my x was a positive number, I ended up with the same number back. But suppose I had the square root of -5 squared. Here, I would square -5 and I would get 25. And then if you remember, when you see this square root symbol, you're assuming that you're taking the principal, right, or the positive square root. So the square root of 25 is actually 5. So in this case, what happened? I started with -5, right? My x is like -5, and I ended up with +5. So bottom line is, whether you start with a positive number or a negative number here, you're going to end up with the absolute value of that number, right, when you evaluate it. So that's why the definition of the absolute value is actually the absolute value of x equals the square root of x squared, right? And there's other instances also where this would be the case. Like, say you had something like the square root of x to the 6th. Well, what times itself will give you x to the 6th? It's actually going to be x cubed. But the problem again with x cubed is, if x is a negative number, it would be negative. So this isn't actually just x cubed, this is actually the absolute value of x cubed.